Hey, what up, everybody? Sorry to be a little late starting, but I accidentally made the Zoom link and I posted it to Geometry Honors because that Google Classroom page was still open from some grading I did last night. I was like, that's weird. It's already 8:16 and there's nobody in the lobby. And then I double checked. Anyway, welcome in. Happy Friday. How's it going?
Good. All right.
Yeah. Any of y'all have any special plans for the weekend?
Project.
Oh, word. What project? What's the deal?
It's for environmental science. For AP environmental science. It's like a choice of projects that you got to pick from.
What are the choices?
Urban planning, making magazines, doing compost, writing an essay on endangered species. That's what we mostly picked. That's what the class mostly picked.
That's cool.
Yeah. Oh, and the environmental pros and cons.
Mr. Robinson, to sum it all up, it's just same as usual
Yeah.
for the week.
Yeah. Well, next week's already the last week of school, so at least there's that. And then y'all can move on to your summer projects yourselves. I don't know what that means. Just because that's different for everybody. But boy, am I excited to have a little bit of like time off of just really no responsibilities, just for a little bit before I start a new job. I'm mostly just excited to, I don't know, stay up late, play Minecraft.
Yeah.
Anyway, let's go ahead and get started. Today we have two warm-up questions using stuff that we've learned about permutations and combinations. Both of these, I hope, are very straightforward. So item number one, there are 16 pool balls on a table, and you know they're numbered numbers 1 through 16. They're unique entities. How many different ways can they be racked up? Yeah, that's the whole question. And my main advice with this is don't overthink it. It would be really easy to overthink this question and come up with some convoluted method that answers it. However, I assert it can be figured out with a single operation. There's just one mathematical thing that has to be assessed to get the answer there to answer one. Item number two, pizza restaurant has 13 toppings available total. And they're also having a special. So you can either get 1 3-topping pizza or 1 2-topping pizza and a salad for $11.99 is the special. And what I want to know is that by the rules of this special, how many different pizzas could potentially apply to this? Again, think about it, set it up, execute, and then we'll go over it. Yeah. Today we'll be having notes on the next section. Today we'll be talking about the binomial theorem.
Mr. Robinson?
Yes?
Do we have a test?
Yeah.
When?
It'll be on Friday.
Friday, we're going to school to say goodbye to the teachers.
You are at, like,
yeah, later.
your time slot's at 11, right?
10.
Yeah.
I think.
Yeah. Then I'll see you there.
Oh, nice.
Yeah, so it'll be 8:15 to 9:15, and then you guys will have plenty of time to get in a car. Yeah, I don't plan on canceling this class. There's also a senior drive-by day next week on Tuesday, and I'm gonna like teach y'all in the morning on Tuesday, and then put on my clothes and head out. I mean, don't get me wrong. Do any of you live so far away that to be at campus by 10, you would have to leave before 9? Is anybody out there an hour? You know what? If you do live a full hour away from campus, send me a chat in the message and I'll figure out accommodations for having a chapter test next week on Friday.
Mr. Robinson, I have a quick question about the warm-up. Can the toppings on the pizza be repeated?
Oh, that's an interesting question. No, let's go with no for the sake of simplicity. So double cheese doesn't count as, or double pepperoni doesn't count as 2 toppings.
Okay, extra pepper.
I muted everybody just to be sure, but it sounds like somebody out there has low batteries in their fire detector. If your fire detectors are beeping periodically, you should probably check and replace their batteries. Or ask an adult in your life to get the ladder out and, you know, have them do it or whatever. Nonetheless, are we ready to go?
Yeah.
Okay. Yeah, okay. So item number 1, there are 16 pool balls. How many different ways can they be racked up? What is the operation that I need to do in order to assess this? This is actually just asking us one thing.
Find the factorial of 5.
And no, so that will give an answer which is way too small. And you're falling into the trap, I believe, of overcomplicating the problem. Could I have another possible response? And like I said, the answer to this is actually radically simple. The trick is that you don't overthink it. So let me ask you this, and this is where I think you might be overthinking it. Where is the 5 coming from? Why would it be 5 factorial?
Because that's what we start off. It goes from 5 in one row, then 4 to 1 in one row, then 3 to, then 2 to 1.
Okay, so that's what I think is probably an overcomplication of this particular problem, is that trying to consider the dimensions of the thing they sit inside of. Sure, it is 5, then 4, then 3, then 2, then 1. But let me go ahead and offer the following remark. When you actually slot the pool balls in, you slot them in one at a time. And what you're effectively filling out is this, right? So I would assert the geometry of the thing that they fit into, it doesn't actually matter. It's not a geometry question. All that matters is the order in which we slot them in. Like, I don't think any possible combination escapes this pattern, right? Of the fact that I'm actually just slotting these pool balls into a position 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 all the way down. So it doesn't matter that it's broken up into individual rows. So what is this actually asking us to do?
Would you have to like multiply 16 and then 11 and then like 7 and then go down as you subtract the amount of pool balls per row?
And again, I like that you're attempting to use the geometry of the rack. No, that's not necessary. That's overcomplicating it, I assert.
Wait, isn't it just 16 times 16 because there's 16 balls and 16 slots to fill up?
And again, no, 16 squared doesn't even begin to approach the number of possibilities that exist here.
Really?
So again, all I'm saying is, kids, this is the pathway upon which I am laying these out. I assert there is no difference to assigning these positions within the rack. I could assign them positions 1 through 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I'm dumb. I lost one somewhere. This last digit here is 16. There's no difference between laying it out this way or taking this curvy line that I have and just laying it out in a straight line. 1, 2, 3, da 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 da, all the way up through 16. What am I actually asking? What matters here? And this is how you want to think about these counting problems. You do not want to overcomplicate this. You want to simply ask yourself one question. Does the order matter? Does the order not matter?
No, it doesn't matter.
Excuse me?
Does,
if the
does
order doesn't matter, then there's only one answer. There's only one way to rack up the pool balls. No matter what, you're going to put 16 pool balls into these 16 positions. Does the order matter or does it not matter?
It does.
It is the only thing that matters. The order matters. And so, of my objects, how many objects do I have?
16.
And how many of them get slotted into the rack?
16 of them.
15.
So what's my operation?
16.
16 permutes, 16 of the permutation of 16.
That is all that this is asking about. It doesn't matter that we're laying them into some triangular rack. What we're asking about is, are they ordered? Is there some orientation to this outcome? And if the answer to that question is yes, it's a permutation. The second thing I'm about to say is much deeper math than that first thing. But the reason why that is true is that no matter what fancy geometry that you are talking about, no matter what way in which you are talking about arranging them, it literally doesn't matter. Any of these rearrangements can be linearized such that all that we're really talking about is the order. When I say that, like, what we're differentiating between using permutations and combinations is, does the order matter or does it not matter? That is hard and fast and true. If the order matters, and it doesn't matter what shape the order takes, but if there is an ordering to it, it's just a permutation, because any fancy permutation can be linearized. Nonetheless, yeah, that means it's 16p, 16. And what are y'all getting out there?
2.09 times 10 to the power of 13. Approximate.
And what is that, chemistry students?
Scientific notation.
This is scientific notation. So this is actually instructing me to move the decimal out 13 digits. So what this is saying is that it's actually 209,227,8,989. So from here, that would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, where I'm not being given these 13 or these last 4 digits by the calculator. Yeah, it's this many, so millions, billions, about 20 billion combinations of ways that you can take the pool's balls on the table, shake them up and put them in that rack. So here's why I find this like devastatingly interesting. If you play pool, if that's a thing that you do, even if you were to play pool consistently every day for your entire life, it is highly unlikely that you will ever rack the pool, the balls right, and get the same order twice. Like, don't get me wrong, if you were to take the time to sort them real quick and put them in numeric order, 1 through 16, sure, you can get that pattern multiple times, like if you do this on purpose. But if you just take the ball, shake them up, fit them into the rack haphazardly, you will probably never get the exact same rack of the pool balls 2 times in your whole life. Isn't that strange?
Yeah, that's crazy. It's kind of strange how you can get such a large number with just 16 balls.
Yeah, well, I mean, this should be the same digit as just 16 factorial, because if you then ask yourself, like, the other way to think about how to arrive here is, well, okay, if these are just positions along the rack, then how many balls could go in this first position?
16.
And then how many balls could go in the second position?
15.
Exactly. So you do that all the way down, and you get that the answer is just 16 factorial. Same thing. And it just so happens that it's hard to grasp simply because we teach you quadratics first, and you're like, oh, that grows faster than a line. That's crazy. And then we teach you exponentials, and you're like, oh, whoa, there's a thing out there that grows faster than quadratics. That's crazy. Yo, factorials grow even faster than exponentials. You very quickly get out of bounds here, and this is just plugging in 16. Nonetheless, item number 2. A pizza restaurant has 13 toppings, and a special has 1 3-topping pizza or 1 2-topping pizza with a salad for $11.99. How many pizzas apply to this special that you need to consider in your brain before you pick one and order? What is my setup?
13 permutation of 3 plus the 13 permutation of 2.
So let's ask first real quick, and I mean, maybe this is a philosophical question. Does the order of the toppings matter? Would you differentiate a pizza where I told you, hey, look at this pizza. Here are the toppings on the pizza. The toppings are pepperoni, jalapenos, and pineapple. Or look at this other pizza. The toppings are pineapples, jalapenos, and pepperoni. Are those 2 different pizzas?
Doesn't matter.
No.
It's exactly the same.
You know, if you're really picky with food, maybe the order in which you put them on does matter. And here's the only reason why I add this additional wrinkle, right? Let's be real. Whichever topping is on the very, very top, that's the one that's going to get crispy. All the ones down below are going to be protected a little bit from heating. So maybe there is a slight difference to the order. But instead of going down that foodie rabbit hole, let's assume we're all normal-ass people. And yeah, let's say that any grouping of a set of toppings is the same pizza. They're going to mix them together and then throw them on top. And so that is to say that the total number of combinations is going to be 13. And then from the set of 13, we're going to choose a combination of 3. And then to that, we also need to add the potentiality that we have 13. And we are going to choose a combination of 2. But in this case, we get a salad, but there is no math for that.
Yeah, it's irrelevant.
And so we take these 2 and we add them up.
Oh.
And you'll notice that since the order doesn't matter, the combination equation produces much smaller outcomes for us. So it's just 286 plus 78, which is equal to 364, which is to say that before you order, you have 364 pizzas to consider, but nobody actually does that because nobody thinks like a computer. You just kind of discriminate or probably default immediately to whatever your favorite set of pizza toppings is, which, by the way, favorite set of pizza toppings out there? Anybody have some hot takes on what constitutes a good pizza? Do you guys not eat pizza?
No,
Okay.
pizza's the best food ever.
Barbecue pepperoni.
Oh, let me instruct you guys, and I don't know if you're ready for this, but
No pineapple on pizza.
oh no, false. No, pineapple is absolutely one of the best
Yeah,
pizza toppings ever. I won't even recommend it though. Here's what you want. There's a set of pizza toppings called the Firefighter, and this is like a fairly common pizza in the northern part of the country, like up around Montana, maybe even all the way out to Washington. It's called the Firefighter. So it's a red sauce pizza with mozzarella cheese, like nothing fancy with the sauce or the cheese. Sauce goes on first, then sauerkraut, then the cheese goes on over the sauerkraut, and then it's topped with jalapenos and like a shaved cured meat. Usually not pepperoni, usually something like even thinner than that. I thought sauerkraut on pizza was going to be the worst, but it turns out sauerkraut on pizza is actually bomb as hell. If you're going to make it at home, I would recommend that you take the sauerkraut and dry it first. Like take it out of the brine and then run it through a strainer and then let it air dry a little bit just so that it doesn't make the sauce all wet. Anyway, are there any questions on the math part of this or on my like really strange pizza preferences?
Nope.
No, okay, great. No, really, wait, I heard a noise right as I started talking. Is there a question? Okay.
I don't think so.
Then today we're going to move on to the second part of our counting principles. Today we're going to talk about a thing which, you know, honestly, it feels weird to sandwich this topic in here. Yeah, it feels weird to sandwich this topic in here. And it seems like why would you ever want to do the calculation that I'm about to show you how to do? This is one of those things where it won't make sense until it's like section 8, when we come back full circle and we talk about this one specific case about flipping coins. It's an important case because it's largely extendable out to other cases of binary information, because a coin itself is a binary system. It only has 2 outcomes, heads or tails. Now that seems like a trivial binary system, but when it comes to like binary at its root, binary is the mathematics that allows your computer to function at all. Binary shows us that all other number constructions, like what math does, can actually be built completely out of zeros and ones without any use for the other digits. And if that wasn't true, the silicon microchip wouldn't work in the way that it does, right? We also see these binary type properties in nature, especially when it comes to the spin of electrons. And there are other more exotic properties that also have a binary nature. It's just that's the only one that we teach to high school students for whatever reason in chemistry. And again, these binary mathematics that we're going to be learning today pertain to that also when it comes to trying to figure out large sets of probabilities. So if you look at today's lesson and you're like, why are we doing this? Just know that these mathematics apply generally to any binary system, and binary systems can be found in the foundations, like the basements of physics and computer science. Nonetheless, today we'll be talking about the binomial theorem. Today we're talking about section 11.6, binomial theorem. And this is a weird union of the following 3 topics. And you're like, what do those 3 things have to do with each other? Here are the 3 things that we're going to be uniting. Today we're going to be uniting a little bit of stuff from counting principles. We are going to take that and we are going to combine something about counting principles with something about polynomials. Also with a little bit of sacred Indian, oh, I'm sorry, capital I, sacred Indian mathematics. And that is to say that a bunch of religions have magic numbers, special numbers, religious days where the digits in the holiday itself have some sort of special meaning, right? Various types of numerology. Turns out there is an ancient piece of Indian numerology that, like, once I show it to you, you'll be like, oh, that's natural. I see why you would write that down. But it relates back to these other two things, polynomials and counting principles. Go figure. And so here's what the binomial theorem does for us. And I'll just like get straight to the chase and then we'll like backfill these other ideas. The binomial theorem allows the rapid expansion of the polynomial of the form quantity x plus y then raised to the n. It is a set of instructions, it's a technique or whatever that allows us to very, very rapidly take this polynomial term here, x plus y to the n, and expand it out. And so here are the bits and pieces of the binomial theorem. So the binomial theorem takes advantage of two things. Thing one, binomial coefficients. Binomial coefficients where the binomial coefficient itself is actually just the combination equation. So any given coefficient that we're about to use in the binomial expansion is exactly the same as NCR, where of course this is equal to the equation n factorial divided by r factorial times n minus r factorial, where in this case, instead of using this to count out actual values in the combination type sense, like instead of saying I have n elements and from them I'm going to select r objects, how many ways can I group that? Instead, what this means is n is going to be the row that we find ourselves in, and r is going to be the entry value. I'll come back to this a little bit later, but just know that we'll be using the combination equation. We'll be using the NCR command on our calculator. And then number two, we are going to use a pattern of exponent summation. That's the second bit that we want to be able to take away today. And this is to say that as we expand out our polynomial, we are always going to end up with a sum of exponents, where as we kind of go along through our terms in the expansion, it will always be such that x to the a, y to the b, plus some next term with a constant, x to the c, y to the d, this will always exhibit the following, I guess, two patterns. A plus b is equal to n. So whatever this initial exponent was in our expansion, the sums of these two exponents should always sum to that exact same value. That would be true of c and d. C plus d will be equal also to n. And as we go across, as we go from term to term to term to term, we usually step down the exponent on x and step up the exponent on y. This is to say that a minus 1 is equal to c, and b plus 1 is equal to d. And you'll notice here that if these two both added up to n before I moved from here to here, then if I decrease a by 1 and I increase b by 1, right? If I drop 1 and I increase the other one, then these two will still have the same sum. That's how this property is achieved up here. That's a bunch of stuff. Let's go ahead and do it manually so that you can see how this pattern kind of arises organically. We'll just do the first, let's say, 3 rows. Yeah, I think we can do the first 3 rows of the binomial expansion manually. So this is to say row 1, or n is equal to 1, n is equal to 2, n is equal to 3. And maybe I'll do some side work so that this can be a little bit nice. Let's do that down here at the bottom of the previous page. So just real quick, what is x plus y to the n? I'm sorry, x plus y to the 1.
X plus.
Yeah, it's just x plus y, right? And luckily, there's nothing to do there. So let's do x plus y squared. What's the rule?
You have to foil.
You have to
X plus
foil it
y
with
times
itself,
x.
and that's why we get interesting middle terms. So the first term is x squared, the last term is y squared, but what's of actual interest to us is that this is actually x plus y times x plus y, right? And when you do first, inner, outer, last, you get the x squared, you get the y squared, but in the middle, you get xy and yx. xy plus yx is equal to 2xy. So that is to say that this term right here is going to be equal to x squared plus 2xy plus y squared. And so let's also do x plus y to the 3 so that we can kind of get a feel for this. And I hope you will accept that this is equal to x plus y squared times x plus y. And the reason why I would rewrite it this way is just to show that this is just going to be equal to the previous line, x plus y squared times another x plus y. So this is equal to x squared plus 2xy plus y squared, then multiplied by x plus y again. And so I can FOIL these two together, and this is going to produce for me a grand total of 6 terms, right? 3 terms by 2 terms. So first I'll multiply in this x, and so this is going to give me back x cubed plus 2x squared y plus xy squared. Then I'm going to go across and I'm going to multiply in the y to these 3 terms to get my other 3. So that's going to be plus x squared y plus 2xy squared plus y cubed. What do you notice about these inside terms, what we can refer to as cross terms?
You can combine them?
We can combine a couple of them. A few of them have identical exponentiation. So right here, this is x squared y, and you'll notice, hey, look, another one, another x squared y. So I can add these 2 guys together, 2 plus 1 giving me back 3. And then the same is true for that other pair. These guys right here, xy squared, can be combined with 2xy squared, again, 2 plus 1, giving us a grand total of 3 for that particular exponent. And so this is to say that if we go through and we combine the like terms, that this is going to be equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. And so I'm going to go back to where I wrote my n equals values, and I'm just going to write out the final answer for each one of these rows so that we can see the presence of the binomial theorem. So this is to say that this first row where n is equal to 1, that's x plus y. This second row is x squared plus 2xy plus y squared. And then this third row is x cubed plus 3x squared y plus 3x y squared plus y cubed. And I'm sorry, let me go ahead and Get rid of those parentheses. They're not really necessary since it's sitting in a row of its own. So here is what the binomial theorem is telling us. And it's a little bit harder to see in row 1. But when it comes to the filling out of this particular binomial expansion, right, taking that binomial term and expanding it very rapidly to large parentheses, right, that a weird pattern kind of arises. So here's pattern number 1. I'm actually going to discuss the pattern of the exponents first, the pattern of exponent summation. Notice here, when n is equal to 1, all of the exponents in this term add up to 1. This is x to the 1 with no y value. This is y to the 1 with no x value. And as I go from here to here, we are decreasing the value of x from 1 to 0, so it disappears, and we're increasing the value of y from 0 to 1 so that it appears. That's not so easy to see. Consider that pattern in play here. We start off with x squared because n is equal to 2. And then as we move to the right, the exponent on x drops by 1. We go from x squared to x to the 1. But to that, we add a y to the 1. So right here, the exponents are just the 2. Here, the exponent is 1. Here, the exponent is 1. 1 plus 1 is 2. And then over here, it's just y squared. Here's where we actually see the pattern doing some work. We have x cubed, x squared, x to the 1, x to the 0. So as we move from left to right, the exponent on x steps down by 1 every step. But in exchange, so that the total is always 3, the exponent of y increases by 1. So we go from y to the 0, y to the 1, y squared, y cubed. Is the pattern of exponent summation okay? We are just looking at a pattern. This might feel a little bit alien because it's not just algebra. We're not just manipulating both sides of an equation the way that we have been for the past few years.
Yeah, that's crazy. I've never thought of it like that.
Yeah, it's about to get a little bit crazier. Yeah. And here's the second part. We have some coefficients. The coefficient here, of course, if nothing is written, what's implied? What's the coefficient on this x?
1.
Yeah, the coefficient here is 1. So this is 1, this is 1. Here the coefficients are 1, 2, 1. Here the coefficients are 1, 3, 3, 1. And here is precisely what is producing or generating these coefficients, like an unambiguous way to say it. Up here, this first coefficient is actually 1c0. And then the coefficient here on y is 1c1. Both of those being the number, well, 1. Up next in the next row, 2c0, 2c1, 2c2. 2c0 is 1, 2c1 is 2, 2c2 is 1. And then down here is where it gets really good. This is going to be 3c0, 3c1, 3c2, 3c3, and this produces the next row, 1, 3, 3, 1. Hot pro tip, the hottest pro tip actually. When you're doing stuff in your graphing calculator, especially for this section, boy do I recommend hitting second entry, which is the thing that I hope you picked up already anyway. So let's say that I'm trying to generate this third row here, right? Such that this is 3 math, C0, okay, just to show that this gives back 1. Let's say that we want to generate out that whole row, but you got to admit this NCR command is buried under some annoying menus. Here's what I can do. I can hit second and then enter. Entry pulls up the last thing that I entered, so it gives me back that last line. And now all I have to do is go back and swap it with a 1, which gives me my 3. Second entry, go back, swap it with a 2. Second entry, go back, swap it with a 3. And that gives me my row 1, 3, 3, 1. Is this okay?
Yep.
So we have two things going on here. Number one, in the act of expanding a binomial, anything of the form x plus y to the n, we can do it very rapidly by relying on a pattern which is established in the first 3 rows here. Pattern number 1. the sum of the exponents is always going to be equal to that n value. But as we go from left to right, the exponent on x drops 1 at a time, while y increases 1 at a time. Drops 1, increases 1, 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 until we're on the other side of the polynomial expansion. And number 2, each one of these is going to be tagged with a coefficient, which can be computed by using the combination equation. And so here's why this is valuable. Even in the generation of this first one, you know, this is kind of tedious. This isn't too bad. At this point, you should be able to do that comfortably and confidently. But this sucks, especially since I know that we're going to take a thing, we're going to multiply it, it's going to expand out to a bunch of terms, and then in the end, we're going to add up all of those terms, and it's going to reduce down to this anyway, right? So let's say that I was going to ask you, please do the following problem for me. Expand x plus y to the 8th. If you were to do that by hand, you would be an absolute sucker, right? If you were to seriously sit there and write out x plus y times x plus y times x plus y times x plus y, yeah, you've kind of missed the boat on this whole binomial theorem thing. Here's what the binomial theorem tells us. First off, how many terms do you think this is going to have in total, this grand total expansion? Notice row 1 had 2 terms, row 2 had 3 terms, row 3 had 4 terms. How many terms is this going to have?
9.
This is going to have 9 terms. So that's one thing that we can take away from the pattern present here in the binomial expansion. And so let me first figure out, well, what's the coefficient on these 9 terms? So to calculate that out, I'm going to go to my calculator, and I'm going to do, well, if n is equal to 8, it's going to be 8c0. And that first exponent is always, or sorry, first coefficient is always 1. So it's going to be 1. And then I'm going to go across and I'm going to calculate all of my other constants. So it's going to be 8c1, 8c2, 8c3. So that's 1, 8, 28, 56. And then I'm going to hit enter again. NC4, NC5. And notice here it's 1, 8, 28, 56, 70. And it's always symmetric. So once you have the left-hand side figured out, the right-hand side is identical. 56, 28, 8, and 1. That's a weird 56. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Great. And now to figure out what the exponents are on each one of them. Well, if this is x plus y to the 8th, then the exponents have to add up to 8 as I go along. So this first one has to be, well, x to the 8th, x to the 7th, x to the 6th, x to the 5th, x to the 4th, x cubed, x squared, x to the 1, and then x to the 0, which I don't write, because what's x to the 0?
1.
1, it just goes away. And then this is going to be y to the 0, y to the 1, y to the 2, y to the 3, y to the 4, y to the 5, y to the 6, y to the 7th, y to the 8th, all on its own. And notice by stepping up 1 for x and down 1 for y as I go along, the sum of any given pair is just 8. 8, 7 and 1 is 8, 6 and 2 is 8, 5 and 3 is 8, 4 and 4 is 8, all sums of 8. And then finally, just add them. And so if you don't believe me, boy, you could dedicate 2 or 3 pages of binder paper to very, very carefully and painstakingly expanding out x plus y to the 8th. Or you could just use the binomial theorem and do it in a single step. Are there any questions there?
Nope.
Okay. And so that hits on items 1 and 2, counting principles and polynomials. Number 1, the binomial theorem is a way that we can expand any polynomial which is written of the form some binomial x plus y raised to the n. And then number 2, the part where counting principles comes into play, is the fact that these binomial coefficients are generated out by the combination equation. However, that last item, that third thing, sacred Indian mathematics, some things important to Hindu religion in general, that's the last item of today's notes, and then we'll have one example. What's the deal with that last part, right? Sacred Indian mathematics. So today we refer to this object as Pascal's triangle. Though it is originally not a French dude's possession, he just happens to be the scientist and mathematician who was working at the time in the 1700s to kind of gain credit for characterizing this thing, though it's been shown that this idea is not his. It's thousands of years old, and the original attribution to its creator has been lost. Here's all that it is. Here's what you do to generate a Pascal's triangle. Though, other interesting thing, if this name seems familiar, it's the same scientist who we named our unit of pressure after. So sometimes when you do chemistry, you talk about like, oh, the pressure of the air is some number of hundreds of pascals. Same guy. Nonetheless, Pascal's triangle is to do the following with digits. 1, 1, 1, 1, 2, 1. And from here, everything else is straightforward. To get the next row, all you do is you add up the 2 digits above it. So right here, this digit is going to be 1. Right here, this is going to be equal to the sum of the 2 digits immediately above it, 3. Right here, this is going to be the sum of the 2 digits immediately above it. Right here, this will just be 1. Next row, 1, 4, 6, 4, 1. Again, each one of these digits simply being the sum of the 2 digits above. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1, da 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 da, on and on and on and on forever. These coefficients in Pascal's triangle are exactly the same as the binomial coefficients. You can see if you take this and compare this real quickly to those first 3 that we expanded by hand, 1, 1, 1, 1, 1, 2, 1, 1, 2, 1, 1, 3, 3, 1, 1, 3, 3, 1. So here's why I bring this up. For whatever reason, and this is a really interesting thing in mathematics, which you can prove should you take the time to do so, the combination equation, right, NCR, produces the exact same set of digits as the digits present in Pascal's triangle. For whatever reason of mathematics, the rule, take the 2 digits above and add them together, is exactly the same as the rule that is defined by NCR. This is to say that this is row 1, row 2, row 3, row 4, row 5. This one right here is row 6, right? So for row 6, here's what these digits are if you wanted to generate them without drawing out the whole triangle. This is 6C0, 6C1, 6C2, 6C3, 6C4, 6C5, 6C6. So depending on like what you're doing with the binomial theorem, if you don't want to use your calculator to generate all those C values, if it's one of these like low digits, or honestly all the way up to row 8, I think this is a fun and easy game to play, filling out Pascal's triangle. If you need all of the digits in a row, you can quickly generate them by using this pattern. Or if you look at the Wikipedia article for Pascal's triangle, they have a really nifty animation of how it's filled out using hexagons, where technically in each row of this, the sum of the digits is just the sum of the two hexagons above. Is this okay?
Yeah.
Okay. Then last example that we'll take these last 5 minutes on is please, especially since we already wrote out Pascal's triangle all the way out here, please rapidly expand and simplify x minus 4 to the 6th. Go. Here are the coefficients, and past that, follow the pattern. I'll give you guys a 60-second head start, and then we'll do this one together. And while you work on this, man, it's super weird. This is completely devoid of context. Like, why is it that we would be so interested with a binomial? Why would you ever want to do this? Like I said, the questions where this stuff will come in very handy are just down the line. When we finally start calculating actual probabilities and stop adding stuff up, this binomial theorem is one of the most powerful tools that you have in your like brain pocket of like mental tools for analyzing gambling games, of figuring out like what are your overall chances of winning and losing. This is one of the best things you can do to very rapidly estimate those odds. Y'all ready for this? Yes, Mr. Rob. Yeah. Okay. So like I said, we could use the combination equation to generate all of the coefficients, or you can just Google image Pascal's triangle to pull a full row of them. And up above, I generated a whole mess of them already. Luckily, here I'm asking for the 6th power, so I know that those are my coefficients. I'm not going to write the ones because we usually don't write like 1x for whatever reason. But this first one here is just going to be 1x plus 6 plus 15 plus 20 plus 15 plus 6. And then again, I won't write plus 1. I'm too cool for that. And then we need to go through and we need to build in our two terms and make sure that they always have the power of 6 in total. So this first one here is easy. That's x to the 6th. And then the other term is raised to the 0. What's my next term? It's going to be x to what power?
5.
Yeah, and I think it's nice and easy to go across and fill out all of the x powers. So 6, 5, 4, 3, 2, 1, which I don't write, and then x to the 0, which I also don't write because x to the 0 is just 1. But what about that other term? So it's not here because whatever it is, it's raised to the 0. What is this going to get multiplied by?
Y to the 1.
There is no y. What is y?
Right, so 4, just 4. 4 to the 1. Oh, negative 4 to the 1.
Y is negative 4. It follows our previous form exactly because x plus y would be to say that this is x plus the number negative 4. And now we can finish our expansion. So this first one is negative 4. This next one is negative 4 squared. This next one is negative 4 cubed. This next one is negative 4 to the 4th. This next one is negative 4 to the 5th. And this final one is negative 4 raised then to the 6th. Again, this has the same tasty feature that the sum of the exponents for any given term is 6, 6, 5 and 1, 4 and 2, 3 and 3, 2 and 4, 5 and 1, 6 and 0. And now all I have to do to make this look like the polynomials that we're accustomed to is, well, simplified. So this is to say x to the 6th minus 24x to the 5th plus 15 times 16, 240. Yes?
No, I was gonna say 240, but
Oh, okay. Do you already have them all?
no.
Next one should be minus
negative
1280 x cubed plus
240
x
never mind.
squared please notice something, and this is important for when you do your homework to make sure you're doing the right thing as you go along. Notice here in my binomial, I had a single negative. Yeah? What do you notice here about the final answer?
The signs alternate.
Correct. And that is a good way to check that you are doing the right thing. If you have a single negative when you're done, the signs should alternate simply because, and this isn't like mystical in any way, it's just because if you have a negative number raised to an odd power, that's negative. If you have a negative number raised to an even power, that's positive. So the negative kind of blinks on and off as you head along. Just one of the implied patterns within the binomial theorem, kind of a special case. But I just wanted to make sure I showed it to you guys once before you do the homework so that it doesn't blindside you. Anyway, that's it for the binomial theorem, and I'm surprised that I finished exactly on time because usually this is a 2-period long lecture. When we come in on Monday, we'll have time, we'll do 2 example questions, and then of course we'll have time to workshop the homework before it's due at 10 p.m. on Monday night. Are there any questions on the binomial theorem? And I'll also post the Pascal's triangle Wikipedia article because it's real interesting. And like I said, I think the oldest reference I've ever seen for this Pascal's triangle notion, right? Like producing new digits by summing the 2 digits up above. The oldest reference I found for it is like 800 BC India. They have like evidence of it being scrawled up on a wall. However, it's such a straightforward notion that like it's been discovered several times independently in different cultures. And you find that to be true with a lot of basic ideas. Like think about the sword, right? Like, oh, I make a stick out of metal, kill enemy, right? That is such like a straightforward notion. It's hard to say it started anywhere, which is why you see the occurrence of the sword in several different cultures independently. Like medieval Europe figured out how to sword at basically the same rate that Japan figured out how to sword. And those swords are different, but they're both still swords. Same with this. This is just such a fundamental mathematical notion that a bunch of different cultures figured it out on their own independently. Wacky stuff. Anyway, y'all have a nice weekend.
Thanks, Mr. Robinson.
Thanks, Mr.
See you next week. See you a week from today. I'll be the guy in the mask. That's how you know it's me.
Mr. Robinson, quick question.
Yes.
How many lessons do we have left for this?
2.
Okay.
Yeah, so in section 7, we'll be talking about calculating actual probabilities, because right now we only know how to count, but on Tuesday, we're going to put that together, and we're going to figure out how to count the numerator of a probability and the denominator of a probability, so that we can say the chance of any particular event happening is blah, blah, blah %. Super useful stuff. It's kind of the foundation of AP Stats, should you happen to take that next year. And then, oh, I'm sorry. I thought this had 8 sections. This book only has 7 sections. We only have 1 lesson left. And that's probability, but we're going to take 3 days on it because it's important stuff.
All right.
Nice.
Yeah. Thanks for asking.
All right. See you then.
Yeah, y'all have a nice weekend.